Hi, Leah. I hope you're doing well again. We're on section 8.5 in the notes, and in 8.5 we're going to be talking about the energy that is calculated when a binary ionic compound is formed. So binary meaning two elements, ionic meaning a metal and a nonmetal. So we're going to calculate the different steps, the energies associated with the different steps in that process, and then get the overall energy associated with that process when the ionic compound's formed, okay? So the whole reason an ionic solid forms is because the ions will have less energy when they're together than when they're separate, okay? So the whole driving force is to lower the energy. So the overall energy should be negative because we're going to release it, okay? The energy released when an ionic solid is formed is known as lattice energy. I don't know where my colors went.
You press the pen. The thing next to the
Pen? Oh, there they are. Thank you. Okay.
You should touch this one.
Okay. So the energy released when an ionic compound form is known as lattice energy. We abbreviate it LE. The greater the lattice energy, the greater the attraction between the ions. I think you have that, don't you? Yeah. You don't have this part, but just stick it in somewhere. And so when we calculate this, the energy associated with forming an ionic solid here, we're going to start with each element in their, what do they call it? There's a word for it. Pure state, I suppose, but that's not the word, but I'll think of it. It'll pop into my head. Yeah, basically in their natural state, but there's standard state is the word for it, okay? So for example, metals in their standard state exist in what phase? Except mercury, solid. And most nonmetals can exist in any state, okay? So remember, we're going to be forming a solid. So there's basically 1, 2, 3, 4, 5 steps, and we gave those 5 steps a name a long time ago. They're called Sybil, all right? So the first step is, oh, it won't let me write there? Why not? Come on, yeah. The first step, oh, because I was white. The first step is to sublime the metal. Because we're going to react these when they're gases. Why? I don't know. That's just how they do it. All right, so we have a solid in this reaction. We're starting with solid lithium, and we're going to make the compound lithium fluoride. But the first thing we need to do is sublime the metal. And that is always going to be your first step with the metal. Unless it's already a gas, you're going to need to sublime it, okay? And they will give you the energy of sublimation. Notice that this energy is positive. That means that this is an endothermic or energy-requiring process. It takes 161 kilojoules to sublime every mole of lithium. That's kilojoules really per mole, okay? The next, since I called it Sybil, the next letter, I, stands for the ionization energy, the energy needed to remove the electron from lithium to make it the ion, right? Because we're going to be measuring the energy of interaction between the ions, so this needs to be an ion. So the next step is the ionization energy of lithium. We're going to remove an electron from lithium, and they'll give you that value. It's 520 kilojoules for every mole. In this equation, there's only 1 mole of lithium, so we're good. All right? The next, the B in Sybil, stands for bond energy. Okay? F is a diatomic in its standard state, right? It exists as 2 atoms stuck together, not 1. So if you think about that, if F is bonded to itself and we want F to react with lithium, what we have to do is break that bond first, right? So the energy needed to break that bond is known as the bond energy. Thank you. All right? And the bond energy, it's given in tables in chapter 8. The bond energy for F to F is 154 kilojoules per mole. For every mole of F2, we're going to need 154 kilojoules to break it. But if you look at the equation, since the coefficient here is 1/2, we only have half a mole. So we divide that number by 2. So all three of these processes so far are energy requiring, which is not looking good for this ionic solid to form. Because in order for formation, you need to lower your energy. And right now, we're putting in energy, putting in energy, putting in energy, right? Okay? The next step is the E. Nonmetals gain electrons. So we need the energy associated with the gain of an electron with F. We have F as an element, it must make F minus. The energy associated with the gain of electron is the electron affinity. Okay? And for fluorine, that's negative. Oh, that means it's exothermic. So here's our first exothermic process. This is exothermic. And then finally, once we have Li in its +1 state and F in its -1 state, we can measure the energy of attraction between them. Okay? They can get together. And the energy of attraction between them, Li plus gets together with F minus, that's the lattice energy, and that value is negative 1,047 kilojoules per mole. So the driving force for this process to happen, since the first 1, 2, 3 steps all require energy, this is this right here. This is the driving force for these two ions to get together, because it releases so much energy. Okay? So if we sum all these energy changes, okay, we get the overall energy change for this reaction. The overall energy change for this reaction is known as the net energy of formation of this compound. We give it the value delta H. Oh, wait. Oh, got a little crazy there. Delta H degree sub F. The degree means that everybody started in their standard state. The degree also means we're at 25 degrees Celsius and 1 atmosphere of pressure. Because if you change the temperature, you change the pressure, you change the energies. Okay? So to get the overall energy change associated with this reaction, the delta H, that's really what that is. It's the overall energy change associated with the reaction. Starting with the elements in their standard state to them being combined. We just simply add the steps. We add Sybil, all right? So delta H, degree sub F, is S plus I plus B plus E plus L. Okay, Sybil. We just add them together. So the energy of sublimation was 161. The ionization energy of lithium was 520. Am I making you dizzy yet? The energy needed to break the bond was 154, but we only have half a mole, so we divided it in half to get 77. The energy needed for F, notice we didn't have to sublime F because it was already a gas, right? So there's no, it's not Sib-Sil, because this is already a gas. There's no sublimation necessary. You need to get them as a gas, you need to make them ions, and then you need to let them get together. Okay, those are really the 3 basic steps. So then we need to make F an ion, which is our E, which was what, negative 328. And then we let them interact, which is our lattice energy, and that is negative 1047. So to get the overall energy of formation, the overall energy change associated with this whole process, you just simply add them. And you get, what is it, negative 333, oh, nope, wrong one, negative 617. And that's kilojoules for every mole of LIF. Okay? Those are your steps. Hi, good morning. How are you?
Good.
You need answers for the homework. Phys ed?
Yeah.
What?
That's where I was.
Why?
Because I had to drop off all my hockey stuff.
Okay. Questions? All right, let's do another one. I know it's like, yeah, it seems easy enough, right? It really, you just add them together. The only thing, though, they might do, the only trick they would do with this is they might give you this. They might give you the overall energy change associated with this practice and then ask you for one of the other values, right? They'll just move the unknown. Let's take a look at the next problem here. Sample problem number 1. Do you have it at the bottom of your paper there? Yeah, okay. It says, given the following data, determine the delta H sub F degree for LIBI. Okay, so first thing you want to recognize is, oh, there's no trick in this problem, right? They're asking me for the overall. They're asking me for the delta H. This is the overall. If they ask you for the overall, it's simply civil. Okay? And they give you, they list all the stuff. Okay? So first step, we need to sublime the metal, right? Sublime. And who's our metal? Li. So we're going to take Li solid and turn it into Li gas. And they gave us the energy associated with that sublimation. See it there? Energy of sublimation, it's 161. This is likely to be a multiple choice question, right? You could see, you could do all this without a calculator. That wouldn't be a big deal. Next thing we need to do is ionize the metal. That's the I. Ionize the metal. Right? S-I. If we're ionizing metal, metals are losers. We're removing an electron from our metal. So we're taking our gaseous lithium, putting in some energy, we know how much, and turning it into lithium +1 ions. And, you know, the electron goes away. That's the reaction for ionization energy. So the ionization energy for lithium is 520. We know that number. Okay? I really want you to write all this out. I don't want you to just like write down the numbers. I want you to understand where it's coming from. Next thing we have to do, our B, is break our bond, if necessary, between our non-metal. B is for bond. So in our equation up here, right, this is diatomic. So really this is Br bonded to Br. What we have to do in order to be able to bond to Br is break that bond, right? Because right now it's bonded to itself and stable. But the idea is that it'll be more stable when it's with lithium than it is when it's with itself. That's why this process will happen. Okay, otherwise, if our delta H, if this number came out to be positive, the ionic compound would not form. It would not. Remember, driving force is to release energy, to lower your energy state. Okay? This would not form if this were positive.
They ask you that?
They may. And we'll get to that later in chapter 6 and 16 is thermodynamics, where we talk about the driving forces for processes to happen. Okay? And so, yes, you could kind of see that coming in. You won't get it in a question like this, but you could get it in a different style question. All right, so we need to break the bond. I'm just going to say the Br-Br bond. So we need the bond energy associated with that. The bond energy of Br2 is 193 kilojoules per mole, but we only have half a mole, right? So we're going to take 1/2 times that number, 1/2 times 193. This makes it look like it's negative 520. It isn't. 1/2 times, what was it? Where's the bond energy? 193. Okay. Whatever that value is. And then the E, now we'll have Br by itself. And again, we don't have to turn it into a gas because it's already a gas here. Now we have Br by itself, and we need to make it gain an electron. So that's the electron affinity. And that should be negative. Yep, it's negative 324 kilojoules per mole. And then finally, L, we're going to react our Li plus. It's the lattice energy of Li plus, the energy of interaction of Li plus and Br minus. And again, that will always be negative, right? Because they're oppositely charged. If they're oppositely charged, it'll always be a negative value because that's an attractive force, and attractive force gets a negative. By the way, you already know how to calculate lattice energy. You've already learned how to calculate this one way. Right? Do you remember that? Q1 times Q2 over R. If these are your charges, this is the distance between your ion centers. Coulomb's law. Yep, Coulomb's law, you're calculating lattice energy. Right? So this is positive and this is negative, which means if you have a positive and a negative, your lattice energy will always be negative. Meaning this process will always be exothermic. It will always release energy. Okay? So the lattice energy of Li and Br is going to be negative 787 kilojoules per mole. And so then to get your overall delta H sub F, you add them together. S plus I plus B plus E plus L. Just simply add them together. By the way, I did not come up with Sybil. A student did. Maybe Kelsey Stallman. I'm not really sure. I don't want to give her credit if she doesn't deserve it. So it's 161 plus 590 plus what's half of 193?
520.
Oh, 590 should become 520. Sorry. What's half of 193? 96.5. Plus minus 324, right? Plus minus 787. Oh, well, doesn't matter. And you should get, anybody get it? 333.5 kilojoules, right? Tony, you confused? Okay. Questions?
Will they sometimes give you will they always give you 5 and then ask you to find that, or now I know they won't always give you ionization. They could ask you for the ionization energy, but could they give you Q1 and Q2 for the lattice energy and have you find that and then add it into this, add it into this?
I've never seen that, though I wouldn't see why they couldn't.
Okay.
They'd have to give you the R, though, too. They'd have to give you the distance between the ion centers. Okay, I have not seen one like that. Where I see it more often is they'll give you this, right? Mm-hmm. They'll give you this value and then ask you for one of the other 4. Okay?
Is this the only time that there will ever
5.
be a fraction in a reaction? As a coefficient?
No. Yes.
It's if you add up all the positive values, it's 777, and then the negative values are negative 1111.
Ooh, maybe I feel I should go do some craps or something. 7-Eleven. All right, no, that's interesting. I don't really like craps. I went to Vegas once. I went to Vegas twice actually, and I tried to shoot craps, and I cannot keep the dice in the stinking thing. It's harder than it looks. The dice always bounce out, and people get really mad about stuff like that. Those are some serious gamblers. I just was rolling the dice, and it's not my fault. I am so diesel, and they just jumped out of the thing. It's not my fault. I couldn't control them. All right. That shouldn't be so funny, Tony. I really wasn't joking there. All right. So as we said, lattice energy is this, and don't worry about this K. It's really just this, right? That's lattice energy. And again, this is review, right? We can see from this equation that lattice energy will become more negative or more exothermic when the ionic charges increase. And when the distance between the ions becomes smaller. This This right here is a very common essay question. They love to ask this. They love for you to have to explain why MgO has a greater lattice energy than CaO. Or why MgO has a greater lattice energy than NaF. They love that question. Okay? Love, love, love it.
So
Why? Yeah, go ahead.
basically, you can say that lattice energy will become more negative or increase when the bond is stronger, because those both make the bond stronger.
Well, lattice energy is a measure of how strong the bond is. Okay? So what you would have to say to explain that is, and you're right, but why is it stronger? You have to attribute it to either this or
Tons
this.
of shells,
Well, not necessarily.
less shells.
Yeah.
You
So
can
here,
tell with, distance, right?
right, right. So if you look at MgO and CaO, they have the same charges, right? This is +2, this is -2, this is +2, this is -2. So the reason this has a greater lattice energy isn't due to their ionic charges, because the ionic charges are the same. What it is due to, though, is the fact that Mg is a smaller ion than Ca. And if Mg is a smaller ion, the R will be smaller, which would make a greater lattice energy. Okay? And I would write, if I'm writing an essay, I would write the equation to show that. C equation below, right? The smaller the denominator, the bigger the lattice energy. Okay? However, if we're comparing MgO to NaF, okay, Mg is +2, O's -2, Na's +1, and F's -1. So the reason MgO is greater than NaF is a different explanation. It's because this has greater ionic charges. This has smaller ionic charges. Okay? But they love that. It's going to be like a part. It probably was in your, like from some of the questions I pulled off your test, but I eliminated that part of the question because you didn't know it yet. Questions on lattice energy or any of this? Sybil, lattice energy. Sybil's a good way to think about it, I think. S-I-B-E-L. All right. I know what Evan's going to do is just add the numbers in his calculator and write down an answer. Don't do that. Okay? It's very tempting. Of course, it's easy. But write it out so we know where you're getting your number from. Okay? Yes, sir.
But when you do Sybil,
Yeah.
it doesn't really matter where those numbers are.
No, the order in which they
Yeah.
appear? No, it doesn't. But you just have to remember the steps. So if you'd like to make up another mnemonic for it, it doesn't matter. I just thought that to me makes sense. Sublime the metal, ionize the metal. Break the bond, ionize the nonmetal, put them together. So to me that logically makes sense. Yes, sir?
What's stopping from just adding all the numbers they give you together?
Because number one, you have to divide the bond energy in half, right? And you have to show where you're getting your numbers from. You can't just add all the numbers together. Because otherwise, they don't give you credit on the AP for just an answer. Even if it's right, you don't get any credit. So you must show where you're getting your answer from to show that you have an understanding of the processes. That's really what it's about. It's not about the delta H. It's about, do you understand the processes that must happen in order to form the ionic compound? Okay? So I guess the driving force to stop you from doing that is that you wouldn't get any credit. Okay? If it's multiple choice, add them together. All right? But I think in your homework, I want you to add them together because I want you to get used to Sybil so that you understand and get used to what you have to do. So that when you see this problem, you know, after we've done equilibrium and kinetics and all these other things, you've completely forgotten what the heck they're asking. The more you write it out, the more likely you are to remember it. But if you just punch numbers into your calculator and then go back to look at it later, you're going to be like, what the heck did I do? Where'd this number come from? That's it. Other questions? Going once here? Twice? Okay, bond energies. Yay! Let's move on to section 8.8. I don't know if it's next or not.
What is 8.6?
It's 8-6.
What's 8.6? Lewis?
Partial
Ion
ionic
pairs.
characteristics.
I'll skip that. That's theory, and you're never going to be tested on it. What it basically says is, remember what I said about Taylor? If he's really great at attracting electrons, so much better than me, he could really take this away from me. Well, what they say in this theoretical thing is that really he's not able to do that. There really is never a complete transfer, okay, of electrons. So instead of defining, if we want to be chemically correct, instead of defining an ionic compound as one in a transfer of electrons, where metals lose and nonmetals gain, I mean, basically we can say it. It's kind of like your math thing. You know what I mean? They're going to be so close together that basically you can say they're together for all practical purposes, or whatever that math thing was you were talking about. But I mean, the electron is so close to him and so far away from me that for all practical purposes we can say he took it and I lost it. But in reality, I'm still attracting that electron. So we don't define ionic compounds in the real chemical world as a transfer of electrons. Instead, we recognize an ionic compound by anything whose melted liquid phase or aqueous phase conducts an electrical current. We don't really define it as the transfer of electrons. Because what they say in section 8.6 is that there can never be a complete transfer because I will still always be attracted to that electron. Okay? That's it. So we're skipping that. There's nothing to do on that. There's nothing to prove. Let me find this section here. Expanded octets. Yay! Okay. So this is another section on how to calculate the overall energy change of a reaction. Okay? The overall delta H degrees of F, but we're going to calculate it using different things. They're going to give us different values. So we're calculating the same thing as we were in section, whatever one we just did, 8.5, but this is more versatile because you just don't, this is good in other reactions other than forming an ionic compound. So this is good for any chemical reaction. We can calculate the overall energy change, the delta H degrees of F, using bond energies. What is a bond energy? You remember, Jess? You were like zoned out there. Are you back?
I'm good now.
Okay. Bond energy. Energy needed to break a bond. Same as the energy released when a bond is formed, right? Okay, it's really super easy. Oh, it's right here. Yeah. Bond energy is the and it's underlined in your notes. Okay, of course, if you were on planet Zeldar just now, then you probably didn't know where that came from. So it's the energy needed to break a bond. They are not measured values, as you can see, they are averages. And we make an assumption that bond energy does not depend on the environment when it really does. So they are approximations, but they come really close to other ways. Because there's lots of ways we can calculate the energy change of a reaction. This is just one. And they become pretty close to real values. There is a table of bond energies. I'm not sure if that's the actual page number or not. It's table 8.4. And I think it's on page 351. So you may want to change that 373 to a 351. Okay? So again, we assume these values are not sensitive to their environment, but they really are. But they're still useful because they come very close to the actual value of the energy change in the reaction. All right. You should notice on this table, and I think I have a copy of this table in your notes, though it's going to be very hard to read due to the quality of the copy, that you should notice that a double bond requires more energy to break than a single bond. And a triple bond requires more energy to break than a double bond. And you can see that if you look at usually carbon. This carbon, yeah. Like carbon double bonded to carbon is 614. However, carbon triple bonded to carbon is, what is it, 839. Okay? So you should recognize that too, that shorter bond or multiple bonds require more energy than single bonds. Okay, so how do you do it? How do you calculate the energy? The enthalpy change, just so you know, that's really kind of the same as energy. For our purposes, we can think of it as energy change. And it is your delta H degrees of F, right? This is the equation that we use, though I will admit I don't really use an equation. I mean, I do this, but I don't do it in equation form. What does the sigma mean?
Sum
It's the sum. It's the sum of all the energy of the bonds that have to be broken minus the sum of all the energy that's released when the bonds are formed. Okay? So the key to calculating the heat of reaction, this is your energy of the reaction. That's your delta H. Don't all of these mean the same thing, okay? From the average bond energies is to carefully list all bonds broken and all bonds formed. And then you do, in order to get the correct sign, broken minus formed, okay? And it makes sense. Here, I'll show you. Let's look at this problem. We'll do one sample problem before roll call ends. And it'll be a little bit tricky until we learn how to draw things, and then it will become easier. But I think for this, in this circumstance, it's not all that bad. In your notes, you may be missing a reactant. Does yours just say CH4 plus 2Cl2 goes to make CF2? Well, where's the F? Yeah, I forgot the F. So make sure, will you add in your 2F2 there, please? And these are our reactants. In order to make the products, we must break these bonds, which means we have to put energy in. So we're going to list all the bonds we have to break of our reactants and their associated bond energies. Okay. Double it. So CH4, hopefully you remember, it looks like this. If you think of CH4, what we really have there are 4 C to H bonds. We're going to have to break those in CH4, right? Cl2 looks like this, but we have 2 of those, right? 2. Cl2 is this, and we have 2 of those. So we're going to have to break 2 Cl to Cl bonds. And again, F2 is F bonded to F. We're going to have to break 2 of those. How do I know? Because of this, right? That's telling me how many I have to break. So those are all the bonds I have to break, right? Those are all of my reactants. Now I look up their bond energies. So C to H bond is 413. So 4 bonds times 413 will give me the energy required to break that molecule apart. 2 bonds times what's Cl to Cl? 239, good. And F to F is going to be 2 times 154. So that is, if we add those up, 1652 here, right? And this is 478, and this is 308. We're just going to add those together, the sigma. It's the sum of all the bonds that have to be broken. 2438. Okay? Those are our bonds that have to be broken. In other words, to break down all the reactants, we have to put in that much energy. Okay? It's a lot of energy. All right. Now, let's list the energy that's released when the bonds are formed. Okay? All right, so what we do now is we list all our bonds that are formed. We just do this for the products, right? So it's really reactants minus products here. Let's look at our bonds that are formed. Oh, CF2Cl2. Hopefully you know that C goes in the middle. F, F, Cl, Cl. Carbon always wants to make 4 bonds because it has 4 valence electrons. F has 7, so it'll only make 1 bond. Cl has 7, so it'll make 1 bond. So we're forming 2 C to F bonds in that molecule, and we're forming 2 C to Cl bonds in that molecule. Also, we have H bonded to F up there, don't we? H to F, and we have 2 of those molecules, so we're going to make 2 of those bonds. And then we have H to Cl. Oh, hold on. Let's just wrap this up. And we're going to make 2 of those. So again, we look up their bond energies. C to F is 485, which is 970. C to Cl is 339, which is 678. And H to F is 565, which is going to give you, excuse me, 1130. And H to Cl is 427. Now, this is the energy released, right? That's the energy released. So we add all those up, and you should get 3,632. So we list our bonds we have to break of our reactants. We list our bonds we have to form of our products. And remember, when bonds are formed, energy is released. When bonds are broken, energy is required. So right now, you should see that more energy is being released, right, than required. This is energy required. This is energy released. Which is bigger? Energy released. So what should the sign of your overall delta H be? Negative. So in order to get the correct sign, that's why we do it this way. We take the bonds formed, right, minus the bonds broken. That way we get the correct sign. And you always do it that way. That way you'll get the correct sign for your delta H. Because, that's wrong. Excuse me. Yeah, otherwise we wouldn't get the correct sign. Bonds broken minus bonds formed. And you always do it that way. Okay, you take your reactants basically minus your products. So we do the 2438. Let's just get it down. Minus the 3632. And that will give us our overall delta H, another way to do it, for the reaction. And what did I get? Did you get negative 1194? Kilojoules per mole of the reaction, right? Per mole of the reaction. Every time this reaction takes place, that much energy will be released. Yes?
Don't forget you're recording.
I will not forget I'm recording.
Okay.
All right. When we come back, we'll do another sample problem, and then I'll let you go to work on your homework. All right? Take your roll call break.
Oh, great.